All right, here we're looking at section 10.2, and our learning targets for the section is now we're going to be graphing cube root functions. In the last lesson we looked at square roots, and now we're going to be looking at cube roots. Again, we're going to compare those functions using our average rate of change and then solve some real-life problems involving those cube root functions. So here's what a cube root function looks like. So we're still dealing with radical functions, but my index is 3, right? So our previous lesson we were looking at square roots, where we were taking the square root of things. Here we're taking the cube root of things. So the difference here is we can have negative values on both sides. So my domain and range are going to be all real numbers, which makes that a little bit easier. And I know this because I can have a negative inside underneath my radical sign because, for example, a negative 2 times a negative 2 gives me a positive 4, but I can multiply that by a negative 2 again, which would give me this negative 8 inside. So that's why I can have negatives here with my using that 3, that index of 3. So let's graph this function and then compare it to my parent function. So again, our parent function is always the most simple form of the function. So here I am just subtracting 4 from that. So first I want to make a table of values. So when we're dealing with cube root functions, the x values you generally want to choose are 0, and then positive and negative 1, and then positive and negative 8. Because I know the cube root of 1 is 1, and the cube root of 8 is 2. So now that I have this table of values, I can go ahead and plug those in to my equation and find my y values. So then I go ahead and plot those ordered pairs. Okay, then I draw my line through that curve, and we see our new graph. Okay, so this black graph here is the parent function, and this blue one is the one I just graphed. So really the difference is, the thing that I've done is I've done a vertical translation down by 4 units. Right? So that's really what we're looking at here. And I could tell that from both the graph and from the equation that I was given. So here are a few I want you to try. Do these by creating a table first and then finding those points that you can plot. So now here we're going to graph this negative cube root of x plus 2 and then compare it to my parent function. So again, I make a table of values. Here I've selected these values because I know if I put a negative 2 in here, it will get me 0, and I know the cube root of 0. I put a negative 1 in here because negative 1 plus 2 gives me 1. I used 6 because 6 plus 2 gives me 8, and those are some values that I know the cube roots of. So that's where I picked these values from. So now that I've got these values, I plug them in and I find my y values. Then I plot those points and I draw my graph, right, which looks something like this blue one. Now I can look at either my equation or my graph and determine what transformations I did. So I see here that I have a 2-unit translation to the left, right, because that's underneath, it's with my x, and I also have a reflection in the x-axis of my graph. Right? And these are going to follow the same a, h, and k values that we've been looking at in the last section. So if you missed that core concept in the last section, go back and make sure you have it. So now here's our next example. We're going to let g of x equal 2 times the cube root of x minus 3 plus 4, then figure out my transformations, and then graph this. So here are the things that I noticed. The first transformation I had was this translation 3 to the right of this graph, right? And that's where this 3 is. Then I saw that I had a stretch of my graph by a factor of 2, and that's of course my vertical stretch because it's out front of my equation. Since a is greater than 0, there's not a negative sign here, there's no reflection. Then I had a horizontal translation, so up 4 units there. So now I can make my table of values and then plot those points. So this little light colored graph you see here was my first transformation, which was my horizontal translation. So I moved everything over 3. Then I stretched it, right? That's what this red graph shows, is I didn't move any of this original point. I just stretched my graph vertically. And then I translated that whole pink graph up by 4 units. Okay, so that's what I've done with this graph. And I can see that from both the equation and the graph now that I've plotted those points. So here are some that I want you to try and think about. What would you do with them? What values, which x values would you pick to put in here? Okay, so the graph of the cube root function m is shown. Compare the average rate of change of m which is the graph, to the average rate of change of h of x equals the cube root of 1/4 x over the interval x equals 0 to x equals 8. So again, when we're dealing with average rate of change, I'm going to be finding the slope between the 2 points that I'm given. Okay, so I want to find those points where my x coordinates are 0 and 8. So for m, I estimate using my graph. So I see at 0, I'm going to be 0. And when my x is 8, we're going to say that my y is also 8. So I'm going to use those 2 points. And I see that my average rate of change there would be 1. Okay, so now for function h, which was the equation that I was given, I plug in 0 for x, and then I plug in 8 for x, and I find that I have a 0 and then a 1.3. So then I can go ahead and find the average rate of change there, and I have an average rate of change of about 0.16. So the average rate of change of m is 6.3 times greater than the average rate of change of h. And I can figure that out is because I can take my average rate of change of m and divide it by the average rate of change of h, and that tells me how much bigger, how many times bigger it is. And that's really what we're going to be looking for in these, is not just kind of comparing, but tell me how much more. Like what factor am I multiplying by to get this? Okay, so now here's a different interval for you to go look at that last problem on. So here's another example we're looking at. The shoulder height in centimeters of a male Asian elephant can be modeled by this function. H equals 62.5 times the cube root of t plus 75.8. And remember looking in centimeters here, where t is the age in years of the elephant. Use a graphing calculator to graph the function, then estimate the age whose shoulder height is 200 centimeters. So the first thing I can do is I graph this, right, and I want to enter my equation that I'm looking at, and then for my second equation, and I can do this on Desmos too, my second equation is going to be y equals 200, okay, because that's the easiest way, or I can just put 200 in for h and solve, but that takes a lot of time. So here I just plug in those two equations, and I use either the trace feature, or in Desmos, if you click on like the intersection point, it will tell you where they intersect. So here I see that y is 200, my x is approximately 7.85. So my graphs intersect at about 8 and then 200. So my elephant is about 8 years old. And so I'm asked here to estimate the age in years, right? So I want to round to the nearest year. So now I want you to think about that last problem again and see if you can use the information that we did last time and see if you can find out where to graph each piece of this. So let's look back at our learning targets. First, we graphed those cube root functions. I want you to really look back and find the a, h, and k values and what each one does. This was our big core concept from section 10.1, so if you missed it, go back and find it. Then we compared those cube root functions using the average rate of change. And remember, to find the average rate of change, we're really kind of finding the slope between those 2 points. And then to compare them, we find how much larger is one than the other. How many times larger is it? And then we looked at some real life problems using those cube root functions. So now I want you to go work on your homework for 10.2.